All right, today's lesson in calc is on the mean value theorem, but it's for integrals. Now, we did a mean value theorem in the past for derivatives and also Rawls' theorem, which was a variation of the mean value theorem. But this today is for integrals. If you remember back when we did mean value theorem for derivatives, we were trying to find on a curve where an average slope would match the slope from the beginning to the end. So like when we were doing the mean value theorem for derivatives, if we had a line that curved here and there on a graph, and I was to calculate the secant line, the average slope from here to here, we were trying to find places on the graph, on the curve, where the slope would match that average slope. So like right here, there would have been a point where I matched the average slope. So we were always, as soon as we start saying the word mean value theorem, the word mean itself kind of is associated with the word average. So where we were doing average slope with the mean value theorem in respect to derivatives, today we're going to do an average, but it's an average with area. Because integrals give us area, so we're actually talking about an average area. So the diagram here at the top of the page, notice that we have a curve here. Curve goes up, curve goes down, and we've marked off from A to B, all right? And so if we were to look at this area that we've marked off from A to B, this area has a curved surface. There's no geometric equations going to be able to give it to us. But we now know with calculus, if we take the integral from A to B of whatever that curve is, and right now we'll just call it the function f of x with respect to x, that's going to give us the area under the curve. Okay? So far so good? Good. All right. So if we calculate that, the part that I shaded in blue, that would give it to me. All right. What we're looking for today is we're looking for where can I mark off. So if I come over here to some c, some value that's actually across the x-axis, so c is an x value, what height would I go to where if I mark that off, that new area, which is more geometric, would match the average? What would that average height be where the area of my new box would match the area of the curved? Okay, just kind of see where we're going. All right, so here's what we have. If I were to compare the area under the curve, I have this equation here, which is summarized on the left-hand side. Do you see how it has the integral from A to B of the function f of x dx? This gives me the area under the curve. And that was my blue area that I first marked off that was curved. All right. Look on the other side of the equals. Do you see an f of c? All right, that f of c is actually like my y value, because this is the point c comma f of c, which is kind of like an x and a y. So that's just some other x value. So c is really another x value. So f of c is the function at c, or it's like a y. Okay? Does that make sense if I call that the height? That this f of c is the same thing, f of c. That looks messy. This is f of c. That f of c right here, I'm going to call that the height. So this right here is the height of my red box, which is supposed to be the average line that if I drew it, I would be able to match the amount of area. What about b minus a? If I go to b and a, and I subtract the two, what would that give me in respect to this red box? If the height f of c gave me the height, that'd be the width, wouldn't it? So, do you see where the parts of this came from? All right. So we know that the integral that we wrote on the left represents a curved area, and we know that going to some height f of c times b minus a, which is the width, would give me two areas that we hope to be the same. So all we need to do is be able to find out how high to go. What c value or what f of c value would be the height that I need to go to where I can match the area. So that would be a good average, and it would even out. So it's almost like we want this part that might be a little bit less, and this part that might be a little bit more to kind of be evened out. So this is what we're talking about. So this is considered our average, this line right here. And I'm looking for the average, which is the F of C line. All right. Now, I think pretty much what I did here is I just had the same kind of thing. I was going to say, let's consider our own. And if I marked off A to B, it's going to look very similar. Let's just draw something that curves, 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 curves. Okay. So here's A. Here's B. Here's this area. Again, it's curve, curve, curve. No way that we could actually calculate that. So we know the integral from A to B of this curve, function f of x, that's what I'll label that one, times dx. Of course, that's just the way we write that. This gives me the area under the curve. I'm kind of repeating myself just for the emphasis of making sure that we have established a good foundation and understanding of what we're doing. So if this is the area of the curve, I want to know what C value. So is C going to be here? So if I come up here, would that be a good area? I don't think that one is the one I want. Do you? The one I've drawn? I think that particular C value would put me at a height that would probably be too little. Okay. What if I came over here and I played with a C value right here? Well, that would put me up here. That F of C value is pretty high. I think that area from A to B would be too much. Do you agree? So what I'm looking for is I'm looking for an average. If I can find the right C value, so maybe the C value I'm looking for is somewhere in between. Can I see what I'm trying to do here? I'm trying to find a good average. Okay, so if I take B minus A times the function height at C, that's going to give me the area of the rectangle of what we call the what? Average height. I think I derived on your notes. Don't I have a derived formula from this we can derive? Well, I'm looking for this. I need to know, how high do I go to where I can mark off an average? See what I'm saying? That's really the part that we're looking for. How high do I go? So what I want to do now is I want to imagine solving for f of c. And that's where you have the formula. Is this just a number? Is b minus a just a number? So if I had a number times something, could I divide and get rid of that? So that's how we derive the equation that you see there. So if I divided by b minus a on both sides, I think the derived formula looks like this. Okay, I think this is what it looks like when it's derived on your paper. The function at c, okay, which is the height, the average height, okay, the average height equals 1 over b minus a. Now, why do I say 1 over b minus a? Because b minus a, because it's in the integral and it's in the denominator. So I'm going to basically pull that out like a constant, because that would just be a number. Like that might be 3 minus 2 or 3 minus 1 or 5 minus 2, whatever the a and the b are. So since that's a number, I'm going to represent it as a fraction times the integral from a to b of the function f of x dx. This is really what we're going to be working with today. Okay? So far so good? All right, let's jump in then. Trying to show you and give you a basic understanding. When we did mean value theorem, kind of repeating myself, with derivatives, we were looking for the average value that would give me the slope that matched. Here, the mean value theorem for integrals, I'm trying to find an average value that would help me find the average area that would match the area. Okay. All right, so let's just jump in and do, I guess, example 1. All right. Find the average value. So really, what are we looking for? The average value is our f of c. Okay. On y equals f minus x on the interval from 0 to 4. All right, just for this first one, I'm going to draw it. Just for the first one. So just to kind of make sure that we kind of understand, I'm going to draw it. How would I draw 5 minus x? So we've drawn our image. We know that this equation y equals 5 minus x. We know that this actually has a positive 5 intercept. It goes down 1 over 1. So it actually crosses at positive 5 on the x-axis and y-axis. But I'm actually asking for the area from 0 to 4, not 0 to 5. So what kind of figure do I have? Is that a trapezoid? All right, so I actually have a trapezoid. Do we know how to calculate the area of a trapezoid? So let's just calculate it by hand. Okay, what's the area of a trapezoid? I think it's 1/2 base 1 plus base 2 times the height. All right, how tall is base 1? Well, I know it's kind of, this is not to scale, but if you were at 4, I believe you're only 1 unit high. So I believe that that point right there is actually 4, 1. So we're only 1 unit high right here, so I'll mark that. So this is a height of 1. How high is it over here? 5. So that's going to be 1/2 of 1 plus 5 times a height, which is actually a sideways height. This right here would be a height of what? 4? Right. Okay, so let's just go ahead and calculate the area. What's the area of the trapezoid? So 1/2 times 6 times 4. 3 times 4, which is what? 12. So that would be 12 square units of area. So far, so good? All right, let's just see. Now, we just kind of did that work just so we know what situation we're dealing with. We know what the area is. Now, let's see if we can apply the mean value theorem for integrals to help us find the average value. Here's my end goal. I'm hoping to find out what height, right? What height right here, what f of c value, would allow me to draw a rectangle that would pretty much be the same amount of area. I bet you could predict what it's going to be, because if this is 4 units wide, how high does my rectangle need to be so that I can actually match an area of 12 units? 3. So we know, right, we know that the f of c value that we're looking for is 3 on the x-axis. Let's just see if the mean value theorem gets us that. So I've tried to start with an example where we know what it is, so we can just apply our math. All right. So according to what we just derived, the function is 1 over b minus a, the integral from a to b of the function dx. Okay. Let's just make sure that we can work it out, and that way we know that if it works for something we can calculate easily, we know it should work for any figure that we probably can't, like curves. So 1 over b minus a would be 4 minus 0. All right, the integral is from 0 to 4, and the function is 5 minus x dx. Okay, pretty good so far? So I'm just trying to find, so the average value f of c is 1/4 times the integral from 0 to 4. I'm just repeating myself now. I'm just going to go ahead and do it. I'm not taking up too much time. What's the integral of 5? If you answered, what's the integral of 5? 5x. All right, minus, what's the integral of minus x? There you go. Then we're going to evaluate it from what? 0 to 4. And we have to remember that we do have what? We do have 1/4 out here. So we can actually wait till the end and do 1/4, or we can go ahead and use 1/4 now. I'm going to go ahead and use 1/4 right now. So I'm going to say that that's the same thing as 5 over 4x minus what? X squared over 8, evaluated from 0 to 4. Is that okay? I'm just trying to make sure I take care of that now rather than later. All right, so what's 5 over 4 times, what's my first value? I have to put 4 down there, minus what? 4 squared over 8. And then you have to subtract what? The lower one. You have to put the lower one in here and here. So that's going to be 5/4 times 0 minus 0 squared over 8. So what do we end up subtracting? that whole thing just becomes a big 0. Zeros are easy. Usually, if you have to substitute in zeros, are easy. So what do we get here? Well, 5 over 4 fourths gives me 5 minus, that's 4 squared. 16 divided by 2 is, or 8 is 2. So the f of c value happens to equal what? 3. Does that verify what we guessed from having done it by hand? Okay. Do you see how we apply the function? So I'm looking for an average value, and I can use my integration. Mean value theorem for integrals. You good? All right. Find the average value of y equals x squared plus 1 on the interval from 0 to 3. All right, we can sketch this, and I'm going to go ahead and do that. So if I sketch out x squared plus 1, is it a parabola that went up 1 unit, and it curves up, right? So that should be x squared plus 1, and I need to evaluate it from 0 to 3. So here I go from 0 to 3. Obviously, this area I cannot do by hand, right? I cannot do the area under the curve because obviously it's curved. So I'm going to have to rely on the fact that I have a mean value theorem that's going to help me find the average value. So as soon as I see average value, I need to be thinking, mean value theorem, right? So that's my f of c. So as soon as it says f of c or average value, I'm looking for f of c. So it's 1 over b minus a. Can we go ahead and use it then? That'd be 3 minus what? 0, because this is like your a and this is like your b, from 0 to 3. Okay. The integral from 0 to 3. And the function is what? Plus 1 dx. All right, so that's going to give me 1/3 times the integral. So 1/3 times, what's x squared integral? Is that x to the 3rd over 3 plus what? X. That's it, right? But we're going to evaluate that integral from 0 to 3. Now, I like 0 because 0 goes away. All right. So I'm going to go ahead and multiply through my 3 just to make sure I do that. I'm getting x to the 3rd over 9 plus x over 3. And that's what I'm going to evaluate from 0 to 3. I'm just trying to make sure I don't forget. You can always come back last and do the 1/3 if you want. It's up to you. So I'm going to first of all substitute in what? The upper limit both places. So if I do that, I get 3 cubed over 9 plus 3 over 3. It's kind of nice and neat that it works out this way. Minus, now what? I put 0 in both places. And of course, that's going to give me what? What does this go to? 0. So what do I end up with? 27 over 9, which is 3 plus 1. And the answer must equal what? 4. How high does this predict that I need to go so I can draw the average? I need to go to a height of 4. So that's only 1. So and of course, this is not to scale, but I need to go to a height of 4, which probably would, this is nowhere near scale. So if I went to 4, like right there, this area, a height of 4, would match the area in blue, which of course, I'm sure mine's not at all scale, because that 3, this is height of 1. But you get what I'm saying? That area would be a matching area. Are you good with that one? All right. We're moving on. Mean value theorem for integration, there is at least one c on the interval where the area can be averaged. Okay. Find the average value and then the c. This is asking me for 2 things. When it says find the average value, that's the what? F of c. Then it's asking me for the what? C. Now when it's asking me for the c, that's actually saying it's kind of like the what? The x value. See, f of c value is kind of like the what? The y value. So what's it saying? Okay, you can get the y value. We have a theorem for that. But then you're going to have to do a little extra work to find out what c goes to that y. We can do that. Okay. Let's see if we can just graph this so we get a picture. All right, 9 minus x squared. Do you know what that looks like? It's going to be, goes up to 9, and it's minus x squared. So that's a parabola that turns down. But I don't need all of it. Let's see. What if I put, well, what if I put 0 in for y? I think that crosses at -3. I think this crosses at -3 and +3. So I don't need that all that area. I'm only looking for from -2 to 2. So from -2 to +2, looks like this is the area under the curve that I'm looking at. Okay? All right, so first of all, it says find the average value. We got that. So how do we find the average value? The average value, which is the average value is 1 over b minus a, which obviously what's 2 minus -2? Nope. 4. So that would be 1 over 2 minus -2, which is actually 1/4. Yeah. Integral from what? -2 to 2 of the function 9 minus x squared dx. All right, so when we integrate, we get 1/4, parentheses 9x minus x to the third over 3, and we're going to integrate that from -2 to 2. All right, so next thing we need to do is evaluate the integral at +2 and -2. All right, so we've just inserted 2 into the integral and -2 into the integral, so we're going to finish. I believe you get 9/2 minus, is that 8 over 12? What's 8/12 reduced? 2/3. All right, so that's what we get from the first one, minus, and I'm going to get -9 over 2. And what's a -2 times a -2 times -2 3 times? -8, and then that subtraction sign is going to make it become positive 8/12, which would be 2/3. So far, so good? All right. I believe I'm going to get 9/2 minus 2/3 plus 9/2 minus 2/3. And I'm going to do this the easy way. I'm going to say that's 18 over 2, adding my like fractions. And that's going to be what? Minus 4/3. So that's really like 9 minus 4/3, which is 27 over 3 minus 4 over 3. So far, so good. And if you subtract the numerators, you get 23 over 3, which is the same thing as 7 and what, 2/3? So that predicts that if I go to 23/3, my average value would take me to 23/3. And remember, this one is high as 9. So if I go somewhere in here to 23/3, that area right there would match the curved area. Everybody understand what you see what we're doing here? Okay, so what I've done is I have my first answer, and that says, okay, I've got my average value, but it also said and the what? And the c, which is like an x value. So I'm kind of looking for, well, if I go to a height of 7/3, what is the c values that would go with that? So I'm looking for c values, so go to 7/3 and I touch the graph. That's the c value, and that would be the negative c value. You see what I'm saying? I see I first drew that a little bit wide. Whoops. So I go over here. Yeah. That area would match the other area. So I'm looking for the c value and the negative c value. All right, so what I need to do next to find c, set f of c equal to the equation and solve. Solve for x, which x is the same as what? Let's see. So what was the equation that I was working with? 9 minus x squared. Okay, so I'm going to say 9 minus x squared. Set that equal to the answer we just got, which is what? 23/3. I'm going to end up probably with some kind of yucky looking fraction square root thing. Well, let's just finish it. So if I subtract 9 from both sides, negative x squared, and I believe I can represent that as 27 over 3, negative 27 over 3. So what do I get when I subtract? Negative 4 over 3. Okay. The negatives are going to cancel. The last thing I need to do is take the square root of both sides. So x squared is equal to the square root of 4/3. Technically, I don't even have to simplify it any farther. That's my answer. I could do a little bit more with that. I could say, well, that's the same thing as square root of 4 over square root of 3, which the square root of 4 is what? 2 over the square root of 3. I could even rationalize my denominator by multiplying the bottom and the top of square root of 3, and that would give me 2 square root of 3 over 3. Oh, I did forget one thing. When you take the square root of both sides, the squares cancel, and I also get what? Plus and minus, which I already predicted that'd be a negative side and a positive side. So this is actually okay. So if you were to leave it square root of 4/3 like on an FRQ, totally acceptable. They don't always take it down this far, because the extra few seconds that you're using to do this, you could possibly be moving on to another question. All right. This one. Why don't you draw it on this next one? Why don't you draw it and see what we're looking at? What does the sine curve look like? From 0 to 2 pi. I think it goes up, crosses down, and comes back up. So if I was to talk about the area under the curve, we mentioned this the other day. This right here was considered positive area. And what about this down here? That would be considered negative area. So if I was to actually add my positive and my negative area, how much area do I have? None. So what would be the average value to make that graph have an average of 0? Where would I go? Would I go up here? Would I go down here? Where would I go? I'd go to 0, wouldn't I? So the f of c value, which is the average, would equal 0, because the area, positive plus negative, equals 0. It's a little bit of a trick kind of a question. It did not mention total area, and if I have a positive and a negative, this would be the only place I could draw, and of course I have to end up with 0. So I could go from 0 to 2 pi, but if I don't have any height, 2 pi times 0 still gives me a final area of 0, which is what it has to be. A little bit of a trick question, but just wanted to mention that one. All right, last part of the lesson is actually on the second fundamental theorem of calculus. So we're kind of going to switch gears a little bit. This is kind of sort of almost redundant. It's like they came up with the fundamental theorem of calculus, which allows us to take a curve and calculate the area from A to B, right? Which is something we can't do with geometry equations. But somewhere along the line, someone said, you know, we forgot to mention that if you take the integral, like if you take the derivative, if you take the integral of something, and then you turn around and you take the derivative of that same thing, don't those two things undo each other? You kind of get what you started with, right? Yes. Well, that's pretty much what you see here. Notice that this notation is what? That is what? Derivative notation. This right here is what? Integral notation. So on one hand, I'm taking the derivative after I take the integral. All right? For the sake of actually working this out, we're going to work out the first one. Then I'm going to teach you the shortcut. Okay? So there is a shortcut way to do these, but first of all, let's make sure that we understand why the shortcut works. All right. I'm going to take the integral of t squared minus t. What is the integral? I'm actually going to work on the inside and then come my way out. What's the integral of t squared? T to the third over 3 minus t squared over 2. Now we're going to evaluate this integral. It says from what? 1 to x. It's a little bit unusual, but we can do that. All right? All right, so here we go. I'm going to evaluate the integral from 1 to x. So if I use my first theorem or first fundamental theorem right, I have to put x in here. Then I have to come back and put a what? 1 in here. All right, so let's do that first. So here we go. I'm going to say x is replacing t cubed over 3 minus x is replacing t again squared over 2. Then I'm going to minus what? Minus 1 goes in there. Is that just going to be 1/3 minus 1/2? All right, and if I do that and find a common denominator, that's going to be 2 sixes and 3 sixes subtracted, which would be what? -1/6. If you subtract -1/6, in the end you're going to end up what? Adding 1/6. All right. So I'm going to add 1/6. Are we good? So this, this is what we end up when we do the integral. Now, what does this outside say to do? Now we're going to take the derivative with respect to x of that integral we just did. Okay, what's the integral of x to the 3rd over 3? Well, I'm going to bring the 1/3 out front. Now, or time bring the 3 out there. X to the 2nd, and 1/3 times 3 cancels, right? Minus, what's the derivative of x squared over 2? 1/2, bring the 2 out front, that'd be x. Well, 1/2 and 2 cancels. And then I'm going to have plus, and what's the derivative of a constant? 0. And I end up with x squared minus x, and that would be my derivative, which is respect to x. Now, how does this compare to what was here originally, the function I started with? I want you to compare this to what? It's the same thing with a different letter. Same thing with a different letter. And that's kind of sort of the shortcut. Doesn't that kind of show us that if we take the derivative of the integral, we basically undo and we just get what we started with? So it says note the derivative and integrals combined. So most of the time we replace the letters in the integrals with x's and we're done. Because notice that right here we are taking the integral with respect to what? X. And somehow or another we're always inserting what into the equation? X. So let's just look at example 6. Without doing the integral and then the derivative, without having to go through that, here's t sine t and I have an x up here. What do you think I might end up with? X sine x. Guess what? That's it. That's it.
Does it matter what the box one is?
Usually it's always 0, but no. If you take even if it's a number, what happens if you come back and take the derivative of a number? It always goes away. So once you take the integral, even if you end up with a number, like a constant there, by the time you turn around after that and take the derivative, your constant goes away. Okay? So it says most of the time, so it says replace the integrals with x's and you're done. It actually comes from the x that they introduced. So basically I'm going to replace the x here and here. That's the shortcut. We just showed that it actually works. Even if I do it the long way, it actually works. Let's try the next two. What happens here? Again, x is going to replace what? There. It's the only thing. Again, this one says a constant, but what did we just say happens if you do end up putting a 6 here? By the time you take the derivative of any constants you have, it's going to go away to 0. So what's my answer going to be? 3x cubed plus 1. Okay? So all I do is insert. Now, A represents, guess what? A represents any number. So it's just like 6 or a 5 or whatever. So in this case, x is going to replace what? T in the equation. So guess what my answer is? Secant to the 5th of x squared minus 3. Seems too easy, doesn't it? And a lot of times there's an argument that said, hey, we should have actually made this the first fundamental theorem of calculus. And that other one that we used should have probably been the second. But it's almost like this kind of came up as an afterthought. It's kind of what it seems like. So far, so good? All right. We do have a couple more examples. Now, notice that in every one of my examples, all of the upper limits were just x's. See how up here it's just an x. So I just replaced with x. Just an x. Up here it's just an x. Just an x. So I'm getting ready though. It says if the upper limit of a function is something else besides just an x, then you still substitute it into the function for the letters, but you also multiply by the derivative of that. All right, so guess what? This time I'm going to put x squared. I'm going to substitute x squared where? I'm going to substitute in for t, and I'm going to substitute it both places. So actually I'm going to substitute in, I'm replacing t squared with x squared, which is going to give me x squared squared minus what? X squared. So what used to be t squared and minus t is now x squared squared minus x squared. Now it said we also have to multiply by what? The derivative of the function, which is the upper limit. So what's the derivative of x squared? 2x, right? So let's just resolve this. I have what? X to the fourth minus x squared. Multiply that by 2x. Final answer is 2x to the fifth minus 2x to the third. So there's a little bit of a tweak. As long as it's just an x, you just substitute in an x. But if it's anything else, you have to go ahead and multiply by that derivative. All right. You do example 10. Let's see what you get. All right, and she is correct. You did get 3x, because you're replacing 3x for t, but you have to square it, minus 3x. Then you have to multiply that by the derivative of, so you multiply that by 3. So you got 9x squared minus 3x. Then that has to be multiplied by 3, which gives me 27x to the second minus 9x. All right, so that is pretty much all you really have to know about the second fundamental theorem of calculus. And I think you have homework problem set, is it 23 or 24? 23, problem set 23, I think it's 1 through 8.